We left off on the last video right at the configuration of sodium, and we came up with a configuration of 1s2, 2s2, 2p6, 3s1 just by following the order of the elements in the periodic table and ending right at sodium. In the next example, we'll look at chlorine, which is also on the third energy level, but now we're all the way on the p block. So you'll start from the top and say, okay, you have two elements on the first row, so that's 1s2, and that's all you have on the first row. So you move on to the second row, that will be 2s2. Then you jump to the p block. None of the elements are chlorine, so you go through all of them. So that means that you have now 2p6. Then you move on to the next row, and you have two elements there, so this is 3s2. And then you jump to the p block, and it takes 1, 2, 3, 4, 5 blocks to reach chlorine. So this will be 3p5. And simply by kind of reading the periodic table from left to right and up and down as we have, we basically come up with electron configurations. You may have done this before by using the Aufbau principle and hand rule. And we're going to use hand rule, mind you, still in this class. But the Aufbau principle, in my opinion, is a little bit obsolete in the way in which we order the orbitals. In fact, we have the periodic table already arranging the order of the orbitals for us, so there's no need to bother ourselves with the Aufbau principle. That's my personal opinion. Other instructors may feel differently about it, but I'm of the opinion that if you do have the resources, use the resources, right? So that's kind of what I'm trying to show you right here. So another example, nickel, neutral nickel. Okay, that is on the fourth row, but it lies under the transition metals. So if we start the process, we'll say 1s2 followed by 2s2 followed by 2p6 followed by 3s2 followed by 3p6, and then we do 4s2, and then that's when we enter the Ds. And if we count up until nickel, first of all we have the group number, and we know that two of these columns have been accounted for the S block. So you could actually do the following. Say, okay, nickel is in group 10. Subtract 2 from 10. That will tell you exactly what column you're dealing with. And in case you don't believe me, simply count it. You have 1, 2, 3, 4, 5, 6, 7, 8 columns. So this will be a D8 system. But the number that precedes D8 is not the row number, but rather the row number minus 1. So this will not be 4D8. It would actually be 3D8. So be very careful with that. It's a very subtle change, but it is an important one to keep in mind. All right, to continue the series, let's look at arsenic. So now we're back on the P block, but we're on the fourth row. So starting from the top, we're dealing with 1s2, followed by 2s2, followed by 2p6, followed by 3s2, then 3p6, then 4s2. At this point, we'll go through the entire transition metal series, so this will be 3d10. And to get to arsenic, we go 1, 2, 3 blocks, so this will be 4s2. Excuse me, 4s3. Wow. Yeah, 4s3 for the final configuration of arsenic, right? Counting the number of blocks, 1, 2, 3. Okay, here's another example, rhodium. Okay, we're getting a little bit more funky. Rhodium is on row 5. So basically we do the same thing. We say 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. And then to get to rhodium, notice that this is in group 9. 9 minus 2 will be 7. So we'll have a D7 system, and since we're in row 5, this will be 4D7, not 5D, but 4D7. Okay, so once again, be careful with that. Transition metals, row number minus 1, as far as the quantum number goes. Okay, and here comes one that's a little bit more tricky. Rhenium, Re. That's on the 6th row in the periodic table. If we follow the same approach, we will write 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, followed by 5p6, and 6s2. Now here's where the trick comes in. Up until 6s2, everything was more or less normal, nothing has happened. But the moment we reach barium, what we need to remember is that what follows barium is not hafnium. What follows barium is lanthanum. So we actually have to make the jump down here to the F block. And we need to remember that there's going to be 14 of these elements up until we get to ytterbium. And since this is on the 6th row and these are the F elements, we subtract 2 from the row number. So we don't say 6F14, nor do we say 5F14. What we do say is 4F14, since 6 minus 2 is 4. And that will take care of the entire F block series. At lutetium, that's when we start again with the D count, which basically is this entire empty slot on the D block. We still count it. So we say, okay, this is the 6th row for the D elements. We'll do row number -1. And for rhenium, we're in column 7. 7 minus 2 is 5. So that means that we're dealing with a 5D5 configuration. And as you can see, it's just these last two that you have to be aware of, the 4F14 and the 5D5 that you have to count. All right, now, as you can see, the farther down the table you get, the longer this whole process gets. Luckily for us, there's another way to depict this that's kind of very elegant and nice, and it's called the Noble Gas Shorthand notation. If you look carefully at the noble gases, including helium, helium has a configuration of 1s2. But from that point thereafter, every single noble gas has the configuration something s2, something p6, something s2, something p6, s2, p6, s2, p6, so on and so forth. And so when you look at all the configurations that we have drawn, you will realize that each one of them contains a noble gas configuration within it. In the case of nitrogen, we have the 1s2, which is the configuration of helium. In the case of sodium, we have gone all the way to 2p6, which is the configuration of neon. For nickel, we have gone all the way up to 3p6, which is the configuration of argon. For rhodium, we've gone all the way to 4p6, which is a configuration of krypton. And then for rhenium, we've gone all the way to 5p6, which is the configuration of xenon. So instead of writing them all out as we have now, what pretty much we can do is say, well, those are the configurations of the noble gases. So simply write the noble gas symbol within brackets to basically convey the idea that it is the entire configuration of the noble gas that precedes the remaining portion of the configuration for the element in question. And what this also does for you is something pretty cool. Not only does it simplify the process and kind of shortens the length that it takes to write the configuration, but also depicts two sets of electrons. The ones that are part of the noble gas configuration are the ones we call the core electrons. And the core electrons are there vastly to balance the charge of the nucleus, but they don't actually get involved in the chemical properties of the element. On the other hand, the configuration, the electronic configurations that come thereafter the noble gas configuration are the actual electrons that get involved in the chemistry of the element. These are known as the valence electrons. Okay, so the 4s2, 3d8, those will be the valence electrons of nickel. The 3s1 is the valence electron of sodium. The 3s2, 3p5 are the valence electrons of chlorine. And for rhenium, you have the 6s2, 4f14, and 5d5 electrons. Although, probably for most practical purposes, the 6s2 and the 5d5 are usually the ones that we count as being the valence electrons of rhenium. But nonetheless, anything thereafter your noble gas configuration is what you can consider your valence electrons, and those will be the electrons that are involved in the chemistry of the element itself. Okay, so what I'm going to do in the next video is show you how to draw out the configurations of each one of these atoms. For now, I want to stop the video right here. All of what we've done right now is come up with the configurations of each neutral element, and we have also established the noble gas notation. Okay, so I'll see you in the next video to start talking about the drawings of each one of the electronic configurations.